Hello everybody, this is Antonio Wolf here to give you a little book review. This is a book I've been talking about in some of my videos if you have paid attention. If not, it's okay. This book is Negative Math, How Mathematical Rules Can Be Positively Bent by Alberto A. Martínez. I'll put it on the description of the video for you to check it out. It's only about $12 on Amazon, at least the ebook. So, and it's a really good read. So what's the book about? Well, this is the book that I've been talking about, which led me to think quite a bit more about negative numbers and how problematic they are. And if you're like me, you probably just kind of stand back and say, there's a problem with negative numbers. What? Yes, there are problems with negative numbers. Hard to believe. I mean, usually we all tend to understand that some things are kind of weird in math, sure, yeah, but most of it makes sense. You know, stuff like, say, imaginary numbers may at first not make sense, but, you know, if you watch around the internet, a couple of videos here and there, you know, depending on how good they are, a good explanation could be given as to, you know, what kind of meaning these numbers have in an applicable use. But what you find out as you read this book is that just because things have been given a certain practical interpretation does not clarify what they actually mean as numbers, as quantities, as operations. And because math originally was conceived by many up until about a century ago, you know, at the turn of the 1900s, as the science of quantity, quantities being, you know, real, positive. You know, the lowest quantity you could ever have is zero, zilch, none, and you couldn't have any less. You know, if that is your conception of mathematics, then negative numbers actually do immediately start being a problem, depending on the interpretations that are given. So, I mean, let's just, I'll just go over the general points brought up by Martínez. And so one is that for a long time, when algebra was brand new, it was considered pretty sketchy precisely because of negative numbers and negative operations. For the longest time, the dominant queen of the sciences was, without a doubt, geometry. And, you know, dominant exponent, or, you know, the one who exposed geometry most popularly was Euclid's. You know, Euclid's Elements was the most popular math book ever, which was read for the longest time. And people saw that as, you know, the most certain knowledge there ever was. You know, lines, arcs, squares, everything involved geometry. It seemed pretty unquestionable. It was pretty obvious, evident. You know, once you started playing around with the rules and how things relate, you were like, yeah, that's true, unquestionable. And then comes algebra, and you have these things like weird negative numbers, negative quantities, and the question starts arising, well, you know, what does this really mean? You know, why do we think that we can use these things? And so, let me see. So this question of what does this mean? You know, what do these operations, what do these numbers themselves really mean? So, okay, let's think about it. Negative numbers as, say, negative quantities. You know, when we compare, say, a negative 1 to a positive 1, what things do we normally think of right off the top of our heads? You know, if somebody asks us, which is the larger quantity, we say, well, 1, obviously. 1 is bigger than negative 1. But think about that, and that's weird. That's weird because then somebody asks you, what is a bigger quantity, 0 or negative 1? And, you know, it should catch you off guard, because all of a sudden it's like, you know, it's either no quantity or a negative quantity. But is a negative quantity really smaller than 0? You know, is that what we really mean? Does that really make sense? You know, how can you have a quantity less than 0? It doesn't really. So, you know, we change we change the meaning and we say, okay, maybe negative numbers don't have anything to do with, say, a magnitude size. Maybe it's a different kind of quantity. It's like, say, a debt or an asset. So, a negative one is you have one debt. Regular one, a positive one is you have an asset. Okay, seems to make sense. But when you try to apply these numbers, say, to in general to everything else, do these numbers actually mean anything? And the answer is obviously no. For example, you can't have somebody who's negative 6 feet tall. You can't have a table with negative 3 legs. So these quantities don't always make sense for everything. And that's kind of one of the issues that just keeps popping up with these negative numbers and these negative operations, which is that as general quantifiers, they don't make sense in every occasion. They don't seem to have like an intrinsic meaning that allows us to just consistently say what these things obviously mean. We have to go with very specific situations in which these things make sense, but when you get out of those situations, they no longer make any sense. And so the question is, what do these numbers really mean? If math is the science of quantity, which is the operations and relations of quantity, what do these really mean when we try to convey this in a sense that, a lot of us are convinced, just simply by the fact that everything seems to use math, that somehow math is real. This is most prevalent against amongst people who are physicists. There's a lot of physicists who have this idea that, reality is fundamentally mathematical. The question then is, well, what the hell does this mean when you have weird things like negative numbers? How does that apply to the general reality of things? And so on and so on. So there's the negative numbers as quantities. Suppose we have the negative operation, subtraction. The basic one is subtraction. What does that mean in a real operation? We know what 8 minus 5 means. You have a quantity of 8, you take away 5, you have 3 left. Okay, that's subtraction. When we try to do, say, 5 minus 8, what does that really mean? Can we really think that? Can we actually comprehend that? And if subtraction is what we normally think it is, the answer is obviously no. You cannot take a greater quantity from a lower quantity. That's impossible. It's magic. Even if you attempt to think about this in terms of debts or assets, if I have 5 assets and I owe you 8, you can't take 8 from me. You can only take 5, and then I owe you 3. There's still a remainder of 3, but that's not a negative 3. That's not a negative 3 quantity, neither for me and neither for you. That's a positive quantity. It's not lesser than, it's not a lesser quantity, it's just a different kind of quantity. But, when you think about it as taking away, well, that doesn't make sense. You can't take 8 from 5. Nonetheless, with algebra, we get situations in which that happens. We have that equation, of an x minus whatever, and it's a valid equation. It's written. When you solve it, you get a negative number. Even if sometimes you can just, actually most of the time, you could probably just rewrite that equation to be in a positive relation, so you don't have to say a negative number, plus a positive or whatever. And you could just rearrange it so that the positive comes first, negative comes second. There you go. Problem solved. No need to appeal to some weird thing called a negative number. So, okay. Point of that is, these subtractions don't physically make sense. If you are, doing some kind of measurements, and you need to do an operation for, cutting a piece of wood, and you consider, say, that subtraction, you have a 8-foot long piece of wood, a plank, and you need it to be 5, or you need to be 3 feet. So, you cut away 5 feet and you leave 3 feet long. 3 feet long, sorry. So that makes sense. But you will never, ever run into a situation in which you need to do a, instead of 8 minus 5 equals 3, you will never get a situation where you need to do a 5 minus 8 equals negative 3. It's just never going to happen physically. It's not intelligible, it's not possible. So, does that really have meaning? So going to a little bit of the history of that, how did we come up with negative numbers to begin with? Well, obviously the one place where they would appear, because they were just obviously useful, was banking, to keep tracks of debt. And so, since bankers originally used them, the original reason for why they were legitimately valid as mathematical entities was precisely that, they represented a real relation of quantity, and therefore, we could think about them just kind of we think about debts or assets. So, if you do -2 plus -2 equals -4, that makes sense because you're adding a debt to a debt. You're increasing the debt, therefore, the debt gets bigger. Okay. And then, for example, if you do -2 times 3, well, you're multiplying the debt. You're increasing the debt, therefore, the debt gets bigger. It's a -6. You have a -6 debt. Okay, that makes sense. But when you start playing with signs, weird things start to happen if you try to keep things intelligible in that manner. Because once you start doing, let's say, a +3 times a -3, things start being weird. Because when you think about... Sorry. When you think about that, what the hell does that mean? There's ambiguities. There's deep ambiguities because now there's an ambiguity between the sign and the operation. So, we have a plus sign, which means sum, and a negative sign, which means subtraction. But when you have the numbers themselves signed, there's an ambiguity between does this actually mean an operation or does this just mean something else? Are these numbers with the signs indicative of an operation themselves, or is it indicative of just a qualitative descriptor on top of the pure quantity? So for example, +3 times -2, what does that mean? If that means do the operation of subtraction twice, well, okay, then you do -3 times plus -3, -6. You subtract the positive twice. But if it's -3 times -2 and -2 is just a sign, what does that mean? What do we do? It's like we're multiplying 3 apples times 2 oranges. What does that mean? It doesn't really make sense, when you actually think about it. It really doesn't. There's no reason or rhyme to why the signs relate the way they do. Why does the negative sign transform the positive sign? Why does it always seem to override the positive sign? Where, for example, you have a 3 plus -3, that's a 0 because it's the negative overrides the sum, it cancels it out, and so you have a subtraction. But if you do -3, say, plus 3, plus +3, actually, let me back that up. If you do a -3 plus a +3, what does that mean? -3 plus -3, it's -6. -3 minus -3, 0. 2 minus -2, 4. The negative sign always overrides the positive and the sum. And why should that be? Both the multiplication and summation. That's weird. So those are issues of, the signs and subtractions. Another one that's very interesting is, and it's the one that brought me to this book, is why does negative times a negative equal positive? Why does a positive times a negative equals a negative? Why does a negative keep overriding? Why does it invert? And when you actually think about that, what does that mean as an operation? There's ways to understand it. For example, that is, if you have a negative 2 times a negative 2, that's a positive 4, and that means you have a negative 2 debt, and the second negative 2 tells you to take that debt away, because it's a subtractive operation. So you subtract 2 debts, then you have gain 4. That doesn't really make sense. You would think, okay, if I subtract 2 debts, I've canceled it out, therefore I should have 0, not 4. But I mean, it's thinking in terms of a direct trade. For example, I have 2 debts here, and then if I subtract those 2 debts, it's as if I flipped it around, and now I have plus 2 here. And so in canceling my debt, or in undoing my debt, I haven't simply canceled them out to 0, but I have actually transformed into a gain. Which is an intelligible thing to say, that if I didn't have 4 and all of a sudden I have 4, but now I have, it cancels out my debt, so I still have total 0, I still somehow gained 4 in the process, and I can understand it that way. But notice that requires you to understand the negative signs in completely different ways that are not consistent. One being first as a qualitative descriptor for the debt, and then the second being as an operative function on the debt. And so the negative 2 times a negative 2 is not really talking about the same thing in both numbers. And in mathematics, when you just write out the sentence, the equation, that's not explicit, that's not really said there. We say that for ourselves to try to make sense of this operation, but it really doesn't make sense. For a long time, a lot of people said, well, then, because these negative numbers, stand in for actually positive quantities of some things that, we seem to think are negatives, but in fact they aren't. If you have a debt, that's a positive debt. It's not some negative number out there. You positively owe you owe something to the bank or somebody. So a lot of mathematicians would say at that point, those points before things were settled, would say things like, well, you can actually just rewrite that as positive numbers. Why would you talk about negatives? If we're talking about debts, we'll symbolize them by these positive numbers, and voila, we're done. Case closed. No negative numbers necessary. No questions about it. No need to ask, about quantity less than 0. No need to talk about these word games of debts. We could just do the regular operations as we choose. There is a formal proof that I've seen, which has to do simply with the formality of operations, the rules of operations of mathematics. For example, if you want to prove that negative 2 times negative 2 equals 4, you can state this through an equation which will have negative 2 as part of its solution, the negative 2 times negative 2 as part of its solution. One equation like that is 2 times 3 equals 6. And if you decide to write an equivalent equation where, it's 4 minus 2, that makes 2, times 5 minus 2, that makes 3, equals 6. Okay, so you factor that out, and you get 4 times 5, 20. 4 times negative 2, that's negative 8. Negative 2 times 5, that's negative 10. And then last you have plus negative 2 times negative 2. And you solve that, so you have 6 equals 2 plus negative 2 times negative 2. You cancel the 2 to the other side. You have a 4 equals negative 2 times negative 2. So therefore, by the very formulation of this, negative 2 times negative 2 must equal positive 4. simply because this equation has to be this way in order to work, due to the way that our operations are set up. So the way the multiplication works, we have to get this result. As unintelligible as it is, nonetheless, the formula tells us that this is so. So that's the standard formulaic method to just show you that regardless of whether it makes sense to us, this is just the way the formalism of the mathematics has to work, given the rules of operation that we have. So for example, think about division. If division is, how many times a quantity fits into another, you ask, well, what does 1 divided by negative 1 mean then? How many times does negative 1 fit into 1? If negative 1 is a quantity less than 1, but it's a quantity also different than 1, you're asking how many times an orange fits into an apple. Doesn't quite make sense, does it? If you think about gains and losses, or assets and debts, how many debts go into one asset, that doesn't make sense. Pretty weird. And so perhaps you may want to solve this by saying, okay, by division, that's the whole idea of how many times a quantity goes into another is not the proper way to phrase it. Division is just the formally inverse operation of multiplication. Therefore, when we ask, 1 divided by negative 1, we ask what number multiplies by negative 1 equals 1, therefore negative 1. Okay, but you've redefined what division means, and you've redefined it in such a way that what we were told division was when we were growing up and learning these things, no longer makes sense. It's not really about that, even though it's sometimes, for the most part, it seems to be about that. But once you get to negative numbers, it isn't. Another thing is that with division, if, for example, if negative numbers are quantities that are less than 0, because, a lot of people will just say, well, obviously they're less than 0. It's worse to have, if you have 0 money but no debts, you still have more than somebody who has, a debt of 1 million, for example. Just to bring in something funny about history. With Donald Trump, there's a video, I think it's from The Apprentice, in which once he talks about one of the times he went bankrupt, and how that day, after he came out of bankruptcy court, he was walking with his daughter, Ivanka Trump, and he points to some fucking homeless guy, and he says, that man is richer than we are because, he has no debt, and I'm like millions in debt. And so, yeah, in that sense, it kind of makes sense to us to think, somebody who has debts has even less than us. But, really think about that and it doesn't make sense. When you talk about what you actually have, if you had debts and you have nothing that anybody could take away, you have just about you have as much as somebody who doesn't have debt and has nothing to take away either. It doesn't really make sense. And if you are obstinate in saying that negative numbers are less than 0, or quantities, less than 0, you get to weird things. For example, that suppose that you divide by ever increasing quantities, and you'd have to divide any number infinite times to theoretically, hypothetically, this is in normal mathematics, this is not allowed because it's being defined as impossible. But back then it wasn't yet known or accepted or postulated that way. So they thought, well, if you divided things infinitely many times, you'd basically end up dividing them into nothing. So say 12 divided by infinity equals 0. So if you wanted to produce a negative number from division, you'd have to divide with a quantity greater than infinity. So, a weird paradox came about that negative numbers were somehow, taken to mean that they were quantities greater than infinity, precisely because, because of mathematical formalisms of division and multiplication, the only way to make sense of that, if these were actually quantities less than 0, was precisely that they were also greater than infinity. So that's a pretty bit of a funny historical logic there. Another one is proportion. Some people thought that division was sort of another way to notate proportion, where, for example, 4:2 not as 2:4, because 4 is twice the magnitude of 2, and 2 is half the magnitude of 4. And so, 2 is less than 4, 4 is greater than 2. The relation of a greater quantity to a lesser quantity cannot be identical. But with 1 and -1, this actually did produce, if you saw it in the language of division, that strange absurdity where a greater quantity and the relation of a greater quantity to a lesser quantity is the same relation of a lesser quantity to a greater quantity. That 1 is to -1 as -1 is to 1, because 1 divided by -1 equals -1, and -1 divided by 1 equals -1. So if you think about lesser and greater quantities, even if you don't think that the negative numbers are less than 0, but you would say that -1 is definitely less than +1, this doesn't make sense. Now, if you are clever and you say, okay, well, we're talking about like just the pure quantities, and say like +1 is apples, -1 is oranges, and we say that when -1 is to 1 as 1 is to -1, what we mean is, 1 apple is to 1 orange as 1 orange is to 1 apple, in that we're talking about the quantities, it's 1, so it's therefore the same. But then now the signs no longer mean, greater or lesser quantities. They just mean different kinds of quantities. And, in that they're different kind of quantities, but we're only caring about the quantity, why do we have the sign in the first place? It doesn't make sense. So the sign isn't doing anything there. So obviously that leads to a ton of other issues that are strange. The most famous problem that resulted from negative numbers was imaginary numbers, the square root of -1. Where if you have the equation x squared plus 1 equals 0, to solve for x squared, x squared plus 1 equals 0, it's a valid equation. If you solve that, you get an absurdity. X must equal the square root of -1, but what is the square root of -1? How is that possible? When no numbers that we have in the number line, either negatives or positives, when squared will produce a negative number, because negative times a negative is a positive. So multiple ways that could have just been dealt with. One of them was just saying, well, this is a nonsensical operation, it's impossible, therefore meaningless, and that was it. But then other people just kind of went, well, it seems valid, why don't we just do it? You solve it, and obviously there's no way to solve square root of -1, because there's nothing that we know of that leads to the square. There's nothing that we know of that squared equals -1. But hey, if you decide that you're going to come up with a whole new number that you say will actually do that, even though it's not like any of the other numbers, it's just this mystery number, we call it, you'll call it the imaginary number. All of a sudden, hey, you can. Why? Because, well, you just find it so. All of a sudden, what was unintelligible is now intelligible, because you decided that now there's a number that actually can do this, but it's a different kind of number from positive or negative numbers. And so it's weird, because now this number is not less than, not greater than, and not equal to 0. It's not on the number line, doesn't relate to numbers in any other way. And therefore, it's an impossible quantity, but nonetheless, you're going to say it's quantity, and you're going to operate with it. And it took a long time, where you will get certain weird things like this. There's an example given in the book about, other ways to, reasons why these were called imaginary numbers beyond the x squared. One of them is, for example, if you're asked to do an impossible operation, say, take the quantity or the number 12, divide that up in such a way that you can multiply the factors to 37. Well, the most you can multiply is 6 times 6 from the whole numbers, or rather any number, any real number that is in 12, because 6 times 6 will yield 36, but any different numbers from then on will just yield something less than 36 no matter which way you cut it. But if you're obstinate and you're going to solve this with an algebraic problem, you can solve this in such a way that you will get an imaginary number in the result, such that once you solve it back to the equation, this imaginary number will indeed, this a real number along with its imaginary counterpart summed together will yield 37. So formally it's possible, but obviously with real quantities that's just not possible. And so you can say that yes, definitely those are absolutely imaginary equations, imaginary operations. They just can't be done. Although if you look around nowadays, you'll find quite a lot, overwhelmingly, about talking about explaining imaginary numbers and saying, oh no, it's wrong to call them imaginary, because they're very real. We found how to use them like every other number. We have complex numbers. We can graph them, and we can do some pretty cool, neat operations with them. There's a lot of interesting things that you could do with complex numbers to solve things that were unsolvable, and theorems that are not really possible in other types of numbers, like the real numbers, fractions, blah, blah, blah. And you can actually look stuff up like that. Probably the best channel for that I found is 3 Blue, 1 Brown. They have a lot of stuff on complex numbers and the use of complex numbers and interesting things you can do with them. But then you look at that history and what that means, and the fact that a use was found for these numbers by mapping them, with imaginary numbers vertical, real numbers horizontal, such that when you multiply things or when you sum the imaginaries, it's like a rotating factor where you go and you rotate around the axes by moving around these imaginary numbers, which is neat. It's useful. It's the mathematical formalism works, but this doesn't actually explain anything about what the meaning of the square root of -1 actually is. It's just showing you that there is a way that this formalism came to be used in such a way that it's now useful, even though the elements, the numbers themselves, are utterly unintelligible. Just because you decide that you're going to plot a number on a graph and call it an axis now, does not make that number intelligible. It makes it just a useful operation, a useful symbol with an operation that ends up being useful for other things, but that's not the meaning of the number. That's not its intelligibility. So with coordinate geometry we get a use for complex numbers, and this was actually a pretty popular thing that was actually discovered quite early on, and then slowly became the accepted norm, and then by the 1800s it was just kind of like the overwhelming norm. As far as intelligibility goes, so yeah, many mathematicians were aware of these problems, in which they admitted that the imaginary numbers and the negative numbers as such, when we thought about them in the traditional ways that we had wanted to think about them, such as quantities, or the analogical ways that we wanted to think about them, such as relations, qualitative oppositions, directions, debts, assets, all these other things. The ultimate conclusion that anybody could take from all of these was that these didn't really make sense, that because none of these could consistently apply to all the operations that we were doing with negative numbers and negative operations. Ultimately, all that we could really say is that, yes, okay, fine, if we stick to keep trying to make intelligible sense of these numbers as such, we have utterly failed, and we agree that there's no sense in any of this. But nonetheless, we have a formalism which we can understand as a formalism. We can understand that these are symbols. We can understand that we have rules of combination, and therefore, people like the mathematician Woodhouse, British mathematician, went ahead and said, okay, we'll just go with formalism, right? We can't understand these quantities and symbols as such. Let's give up on that and let's just go with the pure formalism and say it's at least intelligible how we can get these kinds of relations and quantities and units simply through the operations of the relations. And that was that. Going back to the negative numbers in general, the theory of signs is just a lot of weird stuff. Going back to why does a negative times a negative equal a positive? The questions came up with, well, if we have, 5 plus 2, we know what that means. If we have 5 minus 2, we know what that means. But if we just have negative 2, and if we just have plus 5, what does that mean, really? Do we mean 0 plus 5? Do we mean 0 minus 2? And if we do, why would we be subtracting, a quantity from 0? How is that possible? How, you can't take away from 0. 0 is no quantity already. There's nothing to be taken. Therefore, you cannot subtract from it by definition. If subtraction means the taking away of an equal to or lesser than quantity from a greater quantity. So on those grounds, it's, a lot of people came to just say, well, the signed numbers in themselves don't make any sense because, these operation signs are between numbers. They tell us what to do with numbers in relation to some other number. Alone, they don't mean anything. If the plus and the minus signs mean losses and gains, plus for gain, minus for loss. Therefore, if we have a plus negative number, we mean we're gaining a loss, and we have a minus positive number, it means we're losing a gain. And if we have a minus, it means we're losing a loss. Therefore, haha, that makes sense, right? Perfect good sense. Not quite. Martínez gives this really funny example, and he says it's by the French mathematician Carnot. And he says, if you're in a game where 10% of your winnings, go into a donation pot, and you lose 1,000 coins in that game, therefore you gain negative 1,000 coins. What you put into the winnings donation pot, everybody would consider that, somebody say they won 1,000 coins from the person who lost 1,000 coins, they would put in, what for them is negative 100 coins. They take it away from themselves, they put it in the pot. And so the person who lost 1,000 coins, who has negative 1,000 coins, now will say, aha, if I'm going to put in negative, or 10% of what I won, since I won negative 1,000 coins, I'm going to put in negative 100 coins, which means, and if the coins in the donation pot are all the negatives of the people who won, therefore I get to take negative 1,000 coins. I get to take the negative of the negative and therefore give myself 100 coins. So, somebody would go and who's actually thinking things through would say, no, that's nonsense, obviously. You can't actually do that, just because you won negative 1,000 coins, and you give negative 100 coins to the negative 100, to the, say, total negative 1,000 pot that is being put there. It doesn't mean you now get to take the function of the multiplier of saying like a negative 100 times negative 100 equals 1,000 or whatever. Doesn't make sense. So, that analogy ultimately doesn't make sense when you try to apply it to a lot of things. Just try to go to your bank and said, I've lost my debts 100 times, therefore give me that amount of money. It doesn't work that way. The best you could do is you lost your debts 100. You had 100 debts, you lost them 100 times. Now you have 0. That's all it is. Banks think with subtraction and summation, not with multiplication in its weird ways. Although obviously with the negatives, if you do a minus a negative, it's a positive. But say you do 2 minus negative 2, that doesn't give you 4. If you do negative 2 minus negative 2, that doesn't give you 4. That gives you 0, which is the way a bank does it. For example, another one you could say is, well, what if the negative and the positive actually mean directions? And you say negative means move to the left, positive means move to the right. And so, it's like negative 4 plus negative 4 equals negative 8, which means, you move 4 steps to the left, and then move 4 steps more to the left. You move negative 8 to the left, and you move 4 to the right, and 4 to the right, you move 4 to the right. Okay, makes perfect sense. And if you say do negative 4 steps times 4, that's negative 16 steps to the left. And if you do plus 4 times 4, that's 16 steps to the right. Okay, makes sense. And now do negative 4 times negative 4. You move 4 steps to the left. What? Negative 4 times. What does that mean? First, you're talking just about a sign. Now you're talking about our operation. But what does the operation of moving left to the left mean? It doesn't mean move to the right. But nonetheless, negative 4 times negative 4 equals positive 16. So that analogy doesn't work. And then you say, okay, well, let's suppose that the negative sign actually just means, reverse direction. So, the standard given direction of the numbers, neutral numbers, is positive. Therefore, it's move to the right. And if it has a negative before it, it means move to the opposite direction, therefore the left. So you have plus 4 plus negative 4, move to 4, and then move 4 to the left to the opposite direction. Okay, that works out. That's 0. But then you have, for example, negative 4 times negative 4, you move 4 to the left, but, since the operation is the negative, it's, the inverse of the inverse, you're going to actually move 4 to the right, 16 to the right. Okay, so that makes sense. But then think about that as a sum, and you get a negative 4 plus negative 4. You think, okay, that means I move 8 steps to the left. But that's not the case, because negative 4 means move 4 steps the opposite of, what is the given assumption, which is to the right. So you move left, and then you move 4 to the opposite again, and it's the opposite of what you already did. Therefore, you move 4 to the right, and that would be 0. That doesn't make sense. And then there's another cool thing, and I actually came up with this on my own, but then when I read the book, I was surprised to see this, that this was, my boy Kant came up with this, in which Kant said, it's kind of weird that the plus and the minus symbols do not always mean sum or subtraction, because, for example, negative 2 minus 2 equals negative 4, that's a sum. That's a sum of the negative numbers. That's not a subtraction at all. It's negative 2 minus 2 equals negative 4 is the same thing as plus 2 equals plus 4. If the signs are the same, it's always a sum, and if it's different, then it's a subtraction. But it's not a subtraction with the same symbol, because when you're on the positive side of the numbers, the subtractive sign is the negative sign. When you're on the negative side of the numbers, the subtraction sign is actually the positive sign. So now we have an ambiguity between, do the signs actually have an inherent meaning now? Does the plus necessarily mean sum, and does the minus necessarily mean subtraction? Because when we mix the signs, unless we are really, really explicit about what's going on, it's not clear. Unless we want to really write plus, positive 4 plus positive 4 equals positive 8, and negative 2 plus negative 2 equals negative 4, and then you do negative 2 plus positive 3, or positive 3 plus negative 2, you still have issues of, okay, what is the relation of operations here? Why does the operator sign and the quality sign of the negatives have this inverting relation? It doesn't maintain itself. You can't actually maintain that the operators universally mean the same thing, simply because of the way that the signs mix. So that's pretty neat. So can you actually, does the plus universally mean a sum? Does the minus universally mean a subtraction? And there are ways in which it seems that it can, but then there is also the way that once you start mixing the signs, you have to give the relationship of the operators to the signs, and that relationship actually ends up being given through the relation of the signs themselves. So why do you even have the operators in between? And so obviously then, once you have those things under question, that the plus and the minus no longer necessarily mean sum and subtraction all the time, something like plus the positive 3 times the negative 2 no longer means necessarily that you subtract 3 2 times. If you're mixing the qualities, it's bizarre. There's questions of what is this operation really asking of us? Because if you take the same way that the signs work in some sum and subtraction, where for the negatives the positive is the subtraction, and for the positives the negative subtraction, if we take the first number to give us our position within the number line, and the second one to be the operation according to the opposite sign, or in relation to the opposite sign, then you would have a positive inverted by its negative, and you would have a negative inverted by its positive. Therefore, positive times a negative would be negative, and a negative times a positive would be positive, because just as the negative signs always flip, the opposite signs are the ones that are always the negative to the first sign. And that would make sense, but that would make for some really weird mathematics, and that would mess up the order of operations and the way that multiplication is even carried out. So then this also brings up issues of positive numbers, negative numbers, and neutral numbers. There's an operation in mathematics called the absolute value, but the absolute value does not give a signless number. It actually just turns any number into a positive number, when the original intent was precisely that it would turn into a neutral absolute number, which is not a signed quantity. And then you have a new problem of, how do absolute quantities relate to the signed quantities? If you could have like a negative 2 plus just a 2, for example, what does that mean as opposed to negative 2 plus positive 2? That doesn't mean the same thing. They're not the same kind of number. They're not the same kind of relation. So, if you make that distinction, interesting things arise. So anyways, to start wrapping this up, it's interesting to note that the first half of the book is about the history of negative numbers and imaginary numbers, and that this was a controversy all the way up to about like the 1830s, after which people just stopped caring about the issue. People just kind of gave up and said, well, look, it works. We're making so many beautiful new mathematics, and things are so great and advancing that what the hell, why would we give it up? Let's just keep going. And with the fall of Euclidean geometry, at the turn of the 1800s as well, once geometry was unseated from its position as the queen of the sciences, as the most assured knowledge, the main attack base of people who had been against the weirdness of algebra collapsed. Because now geometry was not the hard science that everybody had thought. It too was just arbitrary. Anybody could make weird geometries of however ways they liked. You just had to keep consistent with the rules that you set up. So, okay. And eventually, that too just extended everywhere. People just kind of went, oh, well, formalism is just the case. So long as we maintain our systems consistent, that's all we really can ask for. We give up on giving intelligible meaning, blah, blah, blah. For the rest of us, we were sort of just given the ways of analogies and the tricks of understanding the mathematics that made it seem like it was about, originating in something empirical, that, that there was a real basis for mathematics. And therefore, a lot of us, are frankly mystified and bamboozled and, in awe of mathematics when, weird things from like maths that we cannot understand, supposedly appear in the real world. And, reading this kind of book, brings to light the fact that, maybe that isn't true. Maybe all these weird mathematical Platonists out there, in physics and in mathematics are kind of full of it. Maybe they're full of it, because, it's all about the rules of operation, the ways that you can keep it consistent, and the ways that you can keep extending the systems to forever. You can have relations of quantity, except, it's no longer relations of quantity. They gave up on that. It's just relations of numbers, and whatever numbers are, they're quantities when we need them to be. They're not quantities when we don't. It's not useful for us to bother arguing that they are. Impossible operations don't bother us. One of the arguments in this book is later on, well, if mathematics is not really founded on any physical operations, we should kind of be wary of how good these mathematics, which were not designed for describing the real world, but which are just designed for, being purely formal games. We should be wary about buying into this idea that math is the foundation of reality, that math is going to tell us about reality, because clearly if we can do the square root of -1, and that's an utterly meaningless physical operation, anything that's using anything of the likes of mathematics of that sort begins to very quickly no longer mean anything intelligible. It may produce real results that accord with real things, but the mathematics that go in between do not have to accord at all with a real world operation of translations or movements or even quantitative relations whatsoever. So a lot of the things that come out of theoretical physics are put in question, deep question, because they work themselves out of mathematics, most of it. So it makes you think. Yeah, and it's kind of weird that here's a sort of well, there was a sort of quote in the book, I can't find it right now, I thought I had it written down, about how it's kind of funny that in mathematics, imaginary numbers were understood long before negative numbers were understood. As a matter of fact, negative numbers were ultimately never understood. They're just a form. The operation of signs is just purely formal. There's no intelligibility to it, ultimately. The same thing for operations. So that's interesting. Martínez, the second half of the book is about an attempt as like, well, if we can just make up math, if formalism is true, and it has a chapter in between going on about the history of how new mathematics came about, like quaternions, vector algebra, etc., which no longer use the old rules of algebra, but invented new rules of algebra for new kinds of mathematics. Well, if we can do that, Martínez says, well, then why can't we just create mathematics not for pure mathematicians' sake, but for specific purposes? Therefore, that we have algebras for those specific mathematics, for those specific things that we want to know, and that they obey rules that which, when we ask what does this mean, we actually do know what it means, as opposed to just, well, it's the formalism that works. And so he goes into a really interesting design of a mathematics in which you don't get imaginary numbers, because negative times a negative is a negative, it's not a positive. So you get to have that problem. And you get he does another design, a quick design of a tentative mathematics of pure quantity, in which you will never get negative numbers whatsoever, because the aim is to simply get pure quantities, pure absolute values. So say something like subtraction, which would be difference. I forget what he calls the operation, but it's not. It's an absolute version of subtraction, in which 5 minus 3 and 3 minus 5 are both 2, because what you're asking is not how many times, what do you get left if you take, the first number or the second number from the first. Rather, it's just simply what is the difference between the two, and the distance between a 3 and 5 and 5 and 3 is the number 2, a quantity of 2, or the difference is a quantity of 2. So that ends up being very interesting, and he basically just poses that question, like, if people knew that this was the history of these kinds of numbers, this is the history of mathematics, that fundamentally this is what mathematics has done, how many people would actually begin to ponder the questions of well, maybe we don't have to be waiting around for mathematicians to figure things out that eventually we find ad hoc, arbitrary applications that just happen to work for real things. Why don't we just put the time in to start creating a mathematics of the things that we want to actually describe? And that's an interesting idea. It's an interesting thought. It's an interesting exercise. So if you're interested in this kind of stuff, look into it. I highly recommend it. It's a really good book. For me, it's a 5 out of 5. I am not a mathematician. I had no interest in mathematics for the most part, but I found this book fascinating. So if you're interested, check it out. This has been Antonio Wolf. See you around.